is Alexander Sodin, and he will talk about the density of states for random band matrices.
Okay, thank you very much. I will tell you about the density of states for random band matrices, and this is joint work in progress with Margherita Di Sartori and Tom Spencer. And in a sense, it's a continuation of much older work by Di Sartori, Pinson, and Spencer. So let me start by defining this object, the random band matrices. So in this talk, a random band matrix will be a random operator acting on L2 of ZD, where D in this talk will be either 1, 2, or 3. And well, in one dimension, it will look more or less as follows. We have a band of width 2W, where the elements are relatively large, of the same order of size 1 over square root of W, and all the rest are very small. So this is in 1D. Slightly more formally, I will impose 3 conditions. First, that the entries are independent random variables subject to the condition HUV equals HVU, which we need to make the operator self-adjoint. The second condition is that H of UV are small if the distance between U and V is greater than W, and not very small if the distance is less or equal than W. And third, we need some normalization. So let's say we ask them to have expectation 0 and variance normalized by the sum of HUV of the sum of the variances in each row equals to 1. So the simplest example is when you really have identically distributed entries here and zeros all over, but somehow convenient to have a more general definition. So the conjecture which I would like to discuss is the following. Well, I need first to define the density of states. So we consider the spectral measure mu, which is defined as usual by the integral of f d mu is just equal to the 0, 0 element of f of h for any function f. And then if this is measured as random, since the operator is random, but if we average it over the randomness, we get a deterministic measure, which is called the density of states. And the conjecture is that under some reasonable assumptions on the entries, the density of states is absolutely continuous with the density bounded uniformly as in the parameter when the parameter becomes large. So there are standard results like Wagner estimates which show that in some cases it's absolutely continuous, but the question is whether you can get a uniform bound when the parameter is large. There are much more interesting questions about these random matrices which relate to the spectral measure itself, not to the density of states, but these I think I won't have much time to discuss. So there are several approaches to these kind of questions. One approach is by perturbation theory, and this is what I talked about here a year ago. So the advantage of this approach is that it is applicable more or less in this generality to very general random matrices. The disadvantage that no one knows how to use it to address this question directly. So usually it allows to control the convolution of mu of the density of states with an approximate delta function of width epsilon, and it works when epsilon is not very small. So I think the current record is you can push it to W inverse, but of course this doesn't allow to address this equation. For this you need to let epsilon go to 0 for fixed W. So another approach, and this is based on the supersymmetric formalism, which is due to Wegener, Efetov, and many other people. And there was a work of Fedorov and Mirlin in '94 who applied it to derive various properties of random band matrices in 1D in dimension 1. So unfortunately, or perhaps fortunately, this work is on the physical level of rigor, and since then there has been some attempts to make something mathematically rigorous out of it. So the observation of one of the observations of Dissertori, Pinson, and Spencer in 02 was that there's a concrete spatial case. You basically choose the centers to be Gaussian with carefully chosen variance. If you consider this concrete example, then the formulae in the supersymmetric formalism become especially nice. And then they applied this method to give a rigorous proof of more or less this conjecture in dimension 3. So they proved that in 3 dimensions the density of states is less or equal than a constant when lambda is less than 1.8. So I should mention that my normalization makes most of the spectrum, forces most of the spectrum into the interval -2, 2. So basically they only exclude a small neighborhood of the spectral edge of the edges of the spectrum. So usually theorems are either more difficult as the dimension increases or easier as the dimension increases, but unfortunately here they really use that the dimension is 3. It doesn't work either for larger dimension or for smaller. And so our current activities, we're trying to prove something like this in dimension 1. And the future theorem is that something like this is true in dimension 1. The density of states is less, well, it's a future theorem, so I can state, I can write whatever I want. The density is less or equal than C epsilon as long as lambda is less than 2 minus epsilon for any epsilon. Perhaps we even don't need the epsilon here, but okay. And in the more distant future, we hope to use these methods to gain some understanding of the spectral measure itself without averaging in 1D, which is the really interesting quantity. So in the remaining time, I will try to explain what is the connection between these kind of problems and statistical mechanics, and I will do it in a very toy example. So how do you study a measure mu, especially if it's a spectral measure of some operator? One convenient object is the Stiltiès transform, which is an integral transform which works, which is defined by this formula. So it makes sense whenever z is not real. It's a convergent integral. And basically the challenge is to understand what happens when z approaches the real line. So for example, if you want to show that a measure has bounded density, it is known that the density of mu is just equal to 1 over pi, the imaginary part of mu hat at lambda minus I0. So if you manage to show that this quantity stays bounded as you approach the real axis, you show that the measure is absolutely continuous. Now, why is this convenient in the random matrix setting? This is because more or less by definition mu hat of z is equal to H minus Z inverse 0, 0 element. And so you can put, if you are after the density of states, you put an average here and an average here, and you get a nice identity. And the question what you do with this. And I will try to explain what you can do with this in the case of 2 by 2 matrices. So let's say you have a 2 by 2 matrix H. Have the entries H0, 0, H0, 1, H0, 1, and H1, 1. And let's say these entries are random and independent, and we want to compute the expectation, the mean value of H minus Z inverse 0, 0. So of course you can write an explicit expression for this. It's the average of H1, 1 minus Z times the determinant inverse of H minus Z, but already for a 2 by 2 matrices, if you write this expression, it's not so easy to integrate it over the variables, and it's even less easy if H is an infinite matrix. So what do? We use a trick in the spirit of the Hubbard-Sodin transformation, which works more or less as follows. First, we do something strange. I want to have here a matrix with positive real part, so I write it as minus the H11 minus Z times the determinant inverse of minus IH plus IZ. For now, I didn't do anything serious. And now I write the following identity. I say it's equal to minus 1 over pi square. I still have the average somewhere. H11 minus Z times a quadruple integral dx0, dx1, dy0, dy1 of e to the minus psi star. So I will explain in a second what I'm writing here and why it's not so as bad as it looks. Minus IH plus IZ times psi. So where psi is the vector x0 plus iy0, x1 plus iy1. So I have to answer two questions. First, why it's true, and second, why such a complicated expression can be of any use. So first, why it's true, except for the factor 1 over pi squared, it's more or less obvious, since if you make a change of variables here, this matrix disappears from the exponent, and you only get the Jacobian outside, so you get this determinant. So I only have to explain the 1 over pi square, and I don't want to do it. And the second question, which is perhaps more interesting, why this is of any use. And it is useful since if you look at this expression carefully, write it down in a second, you will see that it's the expression under the integral is a product of terms, and one term dependent on this times another term dependent on this and times another term dependent on this. So it's very easy to compute the average. Right, since this, what is this term in the exponent, is it's psi 0 squared times, minus I. Let's write down just this term without the Z, times H0, 0 plus psi 1 squared H11 plus psi 0 bar psi 1 plus psi 0 psi 1 bar H01. So it's an exponent of a sum, and we get a product of terms. One term depends on one random variable. So it's very easy to compute the average. And the average is of the following form. We still have the terrible integral over psi. This is d psi. But inside we have something of the following form. We have two terms dependent on the psi j's, and one cross term. I write it in a fancy way, but of course there is only one term in this product, dependent on psi j and psi k. And once, and here there is nothing random anymore. We've already averaged over the randomness. So this expression is already reminiscent of statistical sums and statistical mechanics, and somehow this is the starting point of the analysis. So I will make probably two final remarks and stop. One remark is that if you try it for 3 by 3 matrices, for 3x3 matrices, you already need, it won't work directly, since you will have an expression of the following form. It's determinant of a minor h00 minus z times the determinant inverse of h minus z. And this is an expression of the same type as before. You can write a formula for it, but never mind which formula you write using usual integrals, you won't get a determinant with a positive power. So a way out of this uses the so-called is where the supersymmetric formalism comes in. There is a way to introduce a non-commutative algebra which replaces the algebra of functions of psi, where there is some analog of integral for which the Jacobi change of variables work opposite to what we're used to. So there you can write a similar representation for the determinant. So once you do all this, it can be applied to our random band matrix model, and you get such an expression in the spirit of statistical mechanics, and here's where the interesting things, the analysis starts, but I think it's also where my talk ends. So thank you very much.